introduce the second speaker, Istvan Biro from Heliotis AG. He will talk about industrial Submikrometer-Präzisions-3D sensors for fast in-line inspection.
Thank you very much for the introduction. Welcome, everyone. I'm Istvan from Heliotis, and today I will tell you how to get nanoscale inspection down to the factory shop floor using our white light interferometers. So first, I will introduce the company to you and say a couple of words about white light interferometry in general, how that works. After that, we'll transition and we'll talk about the differences between metrology labs and factory shop floor environments and how to actually make the transition to get from one side to the other one. So Heliotis is a company located in Switzerland with on-site research and development as well as design, building, and support facilities. And we produce white light interferometers as the two instruments you can see on the bottom of the screen. So I've been talking about white light interferometry. Let's have a look what that actually is. And as the name says, it relies on the commonly known phenomena of interferometry with one particular fine detail, namely that as a light source, one uses a light that contains more than a single wavelength. Now, if your sample, which is on the bottom of the screen, is illuminated with that light, as well as your reference mirror located on the right-hand side, those return that light onto the CMOS sensor and produce something called interference. It's a very nice pattern which you can record and analyze to recover the surface from. So if you use white light, as I mentioned, every pixel will see something like this. Now, you don't have to understand this in great detail right now. My point is, this curve has a well-defined maxima. This well-defined maxima allows you to measure an absolute height. So in the end, if you take all the pixels into consideration, you will end up with a 3D point cloud of your object. Great. So why do we want to use white light interferometry? What does it help us with? And Heliotis white light interferometers are specifically designed to have a so-called wide dynamic range. What that means? Well, on one single field of view, your target can have shiny spots or very dark spots, but also very sloped spots, and we can still measure it within the same field of view and the same measurement. White light interferometry is inherently tomographic, which means it can protrude into material that is transparent to that certain wavelength. The consequence of that is that we can measure things that are embedded under transparent material, for instance, under transparent plastic. We can also measure layer thicknesses, for example, the thickness of tube walls or glass covers. Our interferometers are also immune to shadowing. And the great benefit of that is that one can measure very deep cavities which are very, very narrow on the entrance. For example, this plug displayed on the bottom. Most of all, white light interferometry is known to be very, very accurate and very precise. And this is shown here. Basically, we can measure nanometer scale scratches on a glass-like surface. So that being said, where is white light interferometry in the very big field of measurement tools available and technologies available on the market? Well, it is a quite precise means of measuring, but it is also very slow. And herein lies the problem. This sounds very much like a metrology lab setup. And indeed, the goal is to take it out of the metrology lab and make it available at the shop floor, integrated into machines. So just to point out the difference, that's a metrology lab, that's a factory. Notice the difference. One has a controlled environment, large bulky instruments, all the time in the world. The other one is fairly busy, and there is a lot of interference from all the machinery around. So it's not an environment you typically like to measure in. Therefore, the approach one takes is entirely different as well. While in the metrology lab, a technician takes all the time in the world and probes an object slowly and meticulously, In a factory, you cannot do that. You have to keep up with the production cycle, and that is typically really fast. So you need non-contact instrumentation that delivers really quick measurements. As I mentioned, the operator is now replaced by several layers of automation. It is very typical that your measurement instrument is now controlled by a PLC, which is then controlled again from a different layer in this hierarchy. Data valuation is different again. You don't have a human interpreter anymore, but you use established, well-known and working machine vision software instead. So how do we get there with interferometry? And the answer is one has to modify pretty much every single component of a classical white light interferometer. And what Heliotis does to achieve this is to develop our own CMOS sensor, which is particularly suited for interferometry. We place that sensor on high-speed camera boards with FPGA-enabled processing, and we write very efficient, well-developed algorithms to calculate the surface and transfer that. Last but not least, we also develop rugged industrial-grade optics to support our measurements. Now, all of these flow into creating an instrument that you see on the right-hand side, the Heliotis H8. But because Heliotis has this know-how in every single step, in every single field, customers can choose to buy individual components from us or the readily made, out-of-the-box instrument. Indeed, we do have customers who, for example, just buy the sensor because it's a custom sensor that you will not find anywhere else in the market, and build their own instrument or their own measurement setup. If they choose to buy the ready-to-go instrument, they can implement that in an at-line scenario, like with the Heli Profiler displayed here. This is also sold by Heliotis. Or they can build it into a machine as a modular inspection tool. Both paths are possible and well supported by us. So I mentioned a couple of challenges to you, and let's address the first and most important one, which is measurement speed. The sensor that we developed, the CMOS sensor, is very special in the sense that it has custom analog electronics at pixel level. This means that interference signals are processed as they are acquired, live. This signal from every single pixel is then brought onto the FPGA, shown in the middle, and that FPGA reunites, combines the information from all the pixels, and calculates the surface. So in the end, what your PC gets, or your measurement system gets, is one 3D image. And this is really fast. This is what allows us to do one measurement in less than a second, typically. To put this into perspective and show you just how great the data reduction is, imagine your cell phone taking data at 30 frames a second. Well, our instrument would take it at 1 million frames a second. That's a huge data rate. And yet, with the approach that I mentioned, we get it down in less than a second to one 3-dimensional image. This makes us up to 1,000 times faster than regular VLI. Second challenge is how to integrate this into a machine. Well, if you want to put this in a machine, you need something modular, and you need something well-defined mechanically. So for this, we offer a compact aluminum casing with readily available mounting holes, very rigid industrial-grade optics, electronics, controllers, which are meant to be put into machine control units powered by standard industrial 24 volts, and rugged industrial-grade cables. We also provide accurate CAD models for all the instruments, of course. Great. So we've put the measurement device into a machine. Now it has to talk to the machine. And for this reason, what we do is implement communication protocols, offer you communication protocols that are standardized, that are well available throughout the industry. Our camera is built on a GeniCam interface. So literally anything that supports GeniCam, which is an international standard, can use the camera. In addition, we support industrial IOs, as well as industrial communication protocols, for example, EtherCAT, And we have a very competent support team who is well able to advise you on an application. Great. We built it into the machine. We can talk to the machine. But no machine is any good if it cannot use the data. So actually, taking that 3D data that we acquired and analyzing it is a very important challenge. And we address that by making our instruments straight built into or fully compatible with major machine vision software, like Adaptive Vision, Matrix Imaging, Halcon. If you look around, you will find them on this expo as well. And we also provide, of course, a custom SDK for those expert customers who want to do the extra mile and develop something really novel. So all of this flows into such an instrument. This is the H8. And as you can see, there is an orange box on that instrument, which is the optical unit, the interferometric unit. Now, this is designed to be replaceable manually. So you literally grab that orange box, pull it off, put on another one, and you're good to go. The nice thing about this is now you have various fields of views. So each individual optics will have a different field of view and a different lateral resolution, but the Z resolution always remains the same, and it's nanometric scale because it relies on interferometry. So it doesn't really matter if you measure now 6.5 by 6 millimeters, or if you measure just 1/4 by 1/4 millimeters, you will still get nanometer Z resolution. Another instrument is the H9, which is built on the same sort of technology, but it is specialized in providing you with larger fields of view and greater working distances. So we have different options from this instrument as well. And as you can see, the fields of view now actually go to about 25 by 25 millimeters. Working distances are available for 50 or for 100 millimeters, so you can be really far off your object. This is especially useful, for example, if you have a large curved object, or if you do some sort of processing where you want to stay clear of that object. So what are our typical applications? Well, there are plenty. They're really diverse. I'm just going to name a couple here for you. For instance, it often comes down to measuring very small geometries, like on metal parts that you see there on the left-hand side, or it comes down to measuring, for example, volume of deposited glue, or certain electronic components on PCBs. However, we can also measure very, very fine surface features. For example, we can measure very fine surface roughness, shown on the top right-hand side, or surfaces that have been treated with a femtosecond laser. Now, those of you who have heard of that technology know those holes there are really, really small. They are really microscale down to nanoscale in depth. Now, we've been talking about very high, very accurate resolution. This is to show you how robust we could make it. So what you see here are two instruments put on large industrial robot arms inspecting an aircraft combustion chamber. That's pretty large. And what you're looking for are hairline fractures, hairline cracks, so cracks of a few micrometers in dimension. And indeed, this is actually used by an industrial partner of ours. The second application is where our machine, actually two of our instruments are built into a machine that produces stamped metal parts. So you can see there is one instrument on the top, one on the bottom. The object passes through them, and the idea is to measure the shape and the thickness of it. And stamped metal means vibrations, lots of vibrations. It is not what metrology likes. And yet, because we can measure so quickly, we are able to get around that and measure the parts successfully. I'm showing you a quick video of the machine running. You can see the measurement rate is pretty high. It's 2 measurements per second, resulting in full 3D volume, including thickness, because we are measuring from both sides. And you can see that the parts are running through, so the instrument is able to keep up with the production rate. Okay. So thank you very much for your attention. And if you have any questions, feel free to ask or just visit us. We have several demos, several experts to answer your questions. Just go there and look for the people with the orange shoes. Thank you very much.
Yeah, thank you very much for this inspiring presentation. I also don't have the questions here. Well, from my side, I always imagined the ferrometry for if you are really looking for the highest precision. And my question is, you showed a couple of applications. What would you say, where's the main focus in application, where you can say, well, we are unbeatable, or this is really the key application for our technology?
There are several domains, actually, and it comes into play whenever you need to measure something really highly resolved, but with good speed. So if you remember that slide where I was showing you all the available measurement technologies, you could see that the technology is inherently very precise. We got it to work fast, so we retain now the precision, but gain speed, which means it is literally any application that is looking for micro to nanometer scales, especially in the Z range. Especially very fine heights can be measured extremely well. At the same time, one distinctive advantage is that we can measure through transparent material. So we can measure layers. We can measure layer thicknesses of, for example, multi-layered glass or multi-layered coatings on certain objects.
Okay.
Thank you.
Thank you. Good. Thank you very much.